Hello everyone. Today we are going to talk about floating point arithmetic division and square root implementing using Taylor series expansion algorithms. So let me start off with why division and square roots are expensive. If we are using subtracting algorithm, subtracting is slow, and a faster way to do it is reciprocal approximation. For example, instead of doing a by b, we will do a into 1 by b. So we are replacing division with subtraction and multiplication, making it faster. In this method, we sacrifice some accuracy. But in the case of reciprocal approximation, it's not accurate. For example, let's say true division for 3 by 3 is 1. Then reciprocal approximation is 3 into a by b, which is 3 into 1 by 3, that is 3 into 0.333. That will be 0.9999. Here we are sacrificing some accuracy in favor of speed. To evaluate reciprocal algorithm, we can use Newton-Raphson division, Goldsmith binomial expansion algorithm. The paper also talks about improved version that uses careful pipeline scheduling. So finally, this paper proposed a method to implement square root until based on Taylor series expansion algorithms into an existing unit.
This is the Taylor series algorithm to evaluate the square root of a floating point number. It uses the reciprocal approximation. The author has implemented in Verilog using the Synopsys design compiler. It uses a processor with a clock rate of 500 MHz. When you compare the size of the present arithmetic unit and the proposed arithmetic unit, the new arithmetic unit with the square root implementation has an area increase of 23.1% total. And when you compare the performance rate, the present Intel Penguin or the K10 compared to the proposed arithmetic unit is slower, or the proposed arithmetic unit is faster in execution with a less clock rate of 500 MHz.
Now you're going to show you an implementation of the Newton-Raphson algorithm, and we're going to show the square root of 62.41, and the exact square root of this number is 7.9, and we're going to show it in 3 stages with different error margins. So the number is 62.41, and let's try with a higher error margin. You'll see that it took only 4 iterations, and the square root is 8.17, which is far from the real 7.9. So let's try it again. We are going to lower the error margin. Let's try with 0.1, and now we are close to the actual square root. That's 7.9 and 7.90, and the difference is only 0.0045. Let's try again with even lower error margin, 0.0001. Now you'll see that we are very close to the actual square root.
Now we are going to show you how we implemented the Taylor series algorithm. In the main function, we are taking the input from the user, and then we are calling the two functions. The first one is the normal root function, which is C and C++, and C and C++ function built-in square root function. We are just using it. For the second one, we are using our implementation for Taylor series from the paper. We just implemented the algorithm, and it's straightforward. Let me show you how it works. Let's say we want to find the value of 27.5. The first one is the C and C++ algorithm. The second one is our implementation of the Taylor series, and see the difference between the results. And this is pretty much it. And thank you for listening. And if you have any question, just ask now. Thank you for listening.